So this paper is the result of a collaboration between researchers at the University of Toronto, Alexey, Khrabrov, and Eyal, Lara, and IBM Canada, represented by Vijay, Sundaresan, and myself. Since neither Alexey nor Eyal could attend the conference due to some last-minute events, the honor to present the paper was bestowed to me. Let's jump straight into it. So as we all know, Java virtual machines rely heavily on JIT compilers to improve the performance of Java applications. But this comes at a cost. In order to function, the JIT compiler consumes CPU cycles and allocates memory for its internal data structures, activities which can interfere with Java applications because compilations, as we know, are performed at runtime. This interference is mostly felt during the startup and ramp-up phase of the application because that's when most of the compilations take place. So let's look at the graph top right. So this depicts the CPU utilization of a JVM running a web application called JITServer. As you can see, while at steady state, this application consumes about half of a CPU, sometimes there are big spikes in CPU utilization as high as 350%, which are caused by the JIT compilation activity. So these CPU spikes can create hiccups in the behavior of the Java application and lower your quality of service, especially in environments that are scarce in computing resources. So you can think of microcontainers. A similar situation happens for memory consumption. The JIT compiler can create footprint spikes that are conducive to out-of-memory scenarios, which can bring down the JVM. So let's look at the graph bottom right. And this shows the memory utilization of the same JTrader 7 application. At steady state, this application uses about 370 megabytes of RAM, but from time to time, there are big spikes in memory usage caused again by JIT compilations. If you want to avoid the out-of-memory scenarios, you have to over-provision the JVM to cover those spikes. But unfortunately, this in turn increases your costs. Moreover, you don't know how big these spikes can be, and they vary in amplitude from run to run because Java, as we know it, it's not very deterministic. So you'd have to run many experiments to determine the maximum size of these spikes, which makes the provisioning task harder. Now, all these disadvantages can be eliminated by using JIT disaggregation. So what is that anyway? The idea of JIT disaggregation is to decouple the JIT compiler from the JVM, let it run in its own process, containerize it, and make it available as a service in the cloud. Of course, more than one client can connect to a single JITServer instance because there is no one-to-one relationship. Later on in the results section, I'll look at how many clients a server can handle. On the picture here, the compiler from the client JVM is crossed out, but I would like to mention that the clients actually retain the capability of compiling locally, just in case the JITServer is not available. So this is a reliability feature. So what are the advantages of such a solution? Well, those memory spikes that you saw on the previous slide are now completely gone. This means that we can use smaller memory limits for our containers, which in turn means cost savings. And these savings are realized even after we account for the memory consumed by the server itself. This is possible because memory consumption peaks from different applications typically don't align at the server. On the CPU front, the JIT compiler no longer steals cycles from the Java application threads. So startup time, ramp up time, and quality of service all improve, especially in constrained environments. Moreover, JITServer compilation resources can now be scaled independently of the Java application resources. So think of this like a microservices solution, but applied at the JVM level. When the clients need to perform lots of compilations, we can bring up more JITServer instances. And when the need for compilation subsides, we can reduce the number of JITServer instances, maybe even down to 0. Finally, provisioning becomes simpler because the user only has to consider the memory and CPU needs of his own application and ignore the needs of the JIT, which, as I mentioned before, are very hard to gauge. As a sidebar, I would like to mention that we have implemented JIT disaggregation in Eclipse OpenJ9, which is a free open source production grade JVM. The code name of the feature is actually JITServer technology. However, it's not all roses, and I can anticipate some questions related to the networking overhead. So let me go to the next slide. So with a remote JIT, the CPU overhead required to perform a compilation does not go away. Instead, it is moved from the client to the server. This has some advantages for the client, as we already mentioned, but from the point of view of cluster-wide CPU consumption, there is no improvement. On the contrary, we now spend more CPU because we also pay for the network communication, which is not cheap, by the way. Another disadvantage is that compilation latency can be higher with remote JIT due to network latency. It's interesting that when you talk to people about JITServer, most of them assume that there is a single network round trip. The client sends a compilation request, the server performs the compilation, and responds back with the compiled body. However, in practice, there are many messages exchanged between client and server during a compilation because the server needs to gather all sorts of pieces of information about other classes, other methods, profiling information, and so on. It's quite unfeasible for the client to anticipate everything the server needs and embed all that information in the compilation request. Yes, JITServer tries to cache as much as it can, but with a dynamic environment like Java, where classes are loaded, unloaded, modified at runtime, caching has its limits. So most of the time you'll see a scenario like in this figure bottom right, where the client issues a compilation request, then the server will compile for a bit, then it may need some piece of information from the client, it will issue a query to the client responds with the desired information. Again, the server does a bit of compilation, maybe it hits another point where it needs some other piece of information, another request is sent to the client, and so on and so forth, until the server manages to send the compiled body back to the client. So all these network round trips add latency, possibly affecting startup time and ramp-up time. In all fairness, the local compilation can suffer even larger delays when running in CPU-constrained environments. On the figure here, I drew this local compilation as a straight line, but in an environment where you don't have enough CPU, then the operating system can schedule out those compilation threads to make room for the application threads. So in some cases, the local compilation can take even longer than in a remote JIT scenario. So the question is, can we do better, despite these drawbacks, can we do better with the remote JIT? So the idea behind improving remote JIT in the cloud stems from the observation that in the cloud, we see many instances of the same application due to horizontal pod auto-scaling. So why not cache the compilation artifacts produced by the remote JIT for a JVM and then reuse them for other JVMs that are running the same code? So this would amortize the compilation costs over many JVMs and at the same time improve compilation latency because we skip the communication and all those back and forth message exchanges. Conceptually, this is a very simple idea, but the implementation is far from simple. So let's see some of the challenges. First, the compiled body typically refers to other classes, methods, or other internal data structures through pointers. And these data structures can be loaded at different addresses in new JVMs, as shown in the figure below. So we need to fix up those addresses before being able to use the cached compiled body. Hence, we need to have some relocation records to take care of those fix-ups. But it gets more complicated. The JIT uses speculative optimization based on the perceived class hierarchy. So let me give you an example here. So let's say that we have an interface call and that the JIT determines that there is a single implementer for that call. The JIT can inline the body of that implementer, and at runtime, if a new implementer gets loaded, we may need to take some corrective action. In our case, we need to have some validation records to make sure that assumptions that are made during the compilation of this cached method body still hold true in the new JVM. And it gets even more complicated. So how can we make sure that two classes in two different JVMs are equivalent? Because class name alone is not going to cut it. So our solution to these problems is to store compiled methods in the so-called serialized format, which adds some serialization records that specify how to fix up the code in another JVM. We have relocation records for updating the pointers. We have validation records for verifying compiler assumptions. And we also have a mechanism for validating that two Java classes in two different JVMs are equivalent. In the end, all validation records and most of the relocation records are expressed in terms of Java classes. So the question becomes, how can we identify classes that are equivalent? The idea here is to store enough information to look up and verify the runtime class in any JVM. Specifically, for each class, we store the fully qualified class name and a secure hash of the entire ROM class, but also any other class on the inheritance chain, including any interfaces that this class implements. As a sidebar here, a ROM class in OpenJ9 parlance, it is the read-only part of a class, and you can think of it as a pre-processed java.class file. And from it, at runtime, OpenJ9 generates the so-called RAM classes, which are internal representations of the Java classes. Moreover, we also store class loaders, which are identified by the name of the first loaded class. So this is a heuristic, but we found that it works very well in practice. And even if it fails, it can only affect performance, but not correctness. So let's look at an example. So say we have a class B that extends class A. We compile a method M2 from class C, which calls M1, which has an implementation in B, but there could be other implementers as well, and they're not shown here. So let's say that the profiler has determined that most of the time, the incoming object is of type B. Then the compiler will inline B.M1 with a devirtualization guard expressed by the two assembly instructions here. So first we compare the type of the incoming object. If this is B, then we continue to execute the inline body of B.M1. If the incoming object is not of type B, then we jump to the slow path, and there we execute the virtual call. When the client receives the compiled version of C.M2, it needs to patch in its own value for RAM class B. So first, it needs to find its version of RAM class B, and then it needs to ensure that its version is equivalent to RAM class B used when the compilation was performed. For that, the server compares the entire inheritance chain, starting from B down to Java lang object. So let's assume that all classes were loaded by the Bootstrap class loader that loaded Java lang object as its first class. The client uses Java lang object name to find the class loader that loaded its first class with that name. And with the class loader in hand and name B in hand, it finds the RAM class corresponding to B, and from there, the ROM class B. It then compares the SHA-256 of its ROM class B to the SHA-256 received from the server, and it does the same for classes A and Java lang object because they are on its inheritance chain. If everything matches, the client patches its own RAM class B over the guard here. I should mention here that not all compilations are subject to caching for a few reasons. The relocatable code is typically 10% slower than code which is tailor-fit for a particular JVM. Therefore, we use it to accelerate the ramp-up of applications, but then a relatively small set of methods that are hotter than the rest are recompiled at higher optimization levels. From our experience, caching compilations at higher optimization levels increases the likelihood of failing validation records and therefore is not worth it. In practice, we observe a cache hit rate of about 70 to 95%, depending on the application. Now, let's look at some performance numbers. So in our evaluation, we used three different web applications. Acne Air, Day Trader, and Spring Pet Clinic. But in this presentation, I'm going to show only Acne Air because the results are relatively similar for the others. We use several machines with 16 CPUs, and all these machines are connected with 10 gigabyte Ethernet, which I consider to be standard for today's data centers. All applications are run in Docker containers, and the default size for our containers is 1 CPU and 1 gigabyte of memory, but for some experiments, we vary these sizes. The server runs on a separate machine. So now let's look at the startup time. So on this graph here, I'm showing the startup time measured in seconds on the y-axis. And on the x-axis, we have different configurations, so different container sizes. Extra small uses containers with half a CPU and half a gigabyte of memory, small with 1 CPU, 1 gigabyte of memory, and so on and so forth for medium and large, doubling the sizes as we go. Let me say that by startup time, we mean the time needed by the JVM to be able to serve requests. For each configuration, we have 3 bars. So the one in blue is the local JIT, no remote compilations here. The one in orange is the remote JIT, but it doesn't use a cache. And in green, we add the cache to the remote JIT. We can observe from the graph that even the remote JIT alone is able to provide decent improvements in startup time. But if we add the cache, those improvements become bigger. So with caching, we can achieve as much as 15% reduction in startup time. And also another observation is that as you go from small containers to larger and larger containers, those benefits decrease because now the local JVM has all the capacity it needs to perform those compilations locally without affecting other application threads. Now let's look at warm-up time. So this is measured in seconds. We define warm-up time as the time needed for an application to reach 90% of its peak throughput. And we apply load just enough to saturate those instances. Remote JIT by itself is very useful in improving the ramp-up time. And by adding the cache, we extract a little bit of extra gain in terms of warm-up time. Why is that? This is because during warm-up, we have a mix of compilations coming from the cache, but also recompilations. Remember that 10% gap from relocatable code. We try to recover that gap by recompiling the code. And those recompilations do not take advantage of the cache. They are consuming cycles at the server. Anyway, the JITServer with cache is able to reduce ramp-up time by up to 87%. How about the system efficiency with respect to CPU cost? Because in the introduction, I told you that this is a problem for the remote JIT in itself. In here, the experiments are conducted such that we run 64 JVM instances that are started at the same time. Actually, no, they are not started at the same time. They have a small gap in between, and they are short-lived. So some of them last for 2 minutes. In other experiments, they run for 5 minutes, and yet in another experiment, they run for 10 minutes. So they are started and stopped all the time. We look at CPU cost, which is defined as the total CPU time, so the JVMs plus the CPU that is consumed by JITServer, and we divide that metric by the number of requests served. As you can see here in the first grouping of bars, remote JIT can increase CPU time for reasons that I explained in the introduction. However, the moment you add the cache, we don't have to perform all the compilations again and again. We can serve directly from cache, and we can save a lot of CPU. So there is a significant improvement in CPU consumed with the addition of the cache. That number comes up to be up to 77% smaller CPU cost with caching. How about the memory usage? So here we see good improvements from the remote JIT alone, and the addition of the cache doesn't provide much. So from the memory point of view, just the remote JIT is good enough. And this, why is this important for the end user? Well, as I said earlier, with smaller containers, you can increase the application density and therefore improve your costs in the cloud. Now, how about scalability? On this graph, I'm showing the full warm-up time, and this is normalized to the situation where we don't use a remote JIT. Therefore, the local JIT is a straight line. If we look at the line in orange, the remote JIT is able to handle about 50 instances before crossing out the local JIT. Whereas if we add the cache, this is the line in green, then we can tolerate even more instances without additional CPU consumption. So the gist of this is that caching allows you to serve more clients using the same amount of resources because the compilation cost is amortized over multiple clients. And finally, let's look at the network latency. How does this affect the performance of JITServer? We run various experiments with increasing network latency up to 8 milliseconds. And we see that remote JIT can tolerate latencies about 3 milliseconds before making a warm-up time larger than when we don't use the local JIT. Whereas if we add the cache, we can tolerate latencies, network latencies that are double in size, so about 6 milliseconds. And I would say that in the typical data center, network latencies should be in that range, maybe even, I've seen on Amazon latencies that are well under 1 millisecond. So this is not something that it's fake in our evaluation. Okay, so that is the last experiment that we've done. In conclusion, in this presentation, we showed that JIT compilation overhead can pose some performance challenges to Java applications running in the cloud, where frequent restarts may be happening. These problems can be alleviated to a large extent with a disaggregated remote JIT. However, this solution tends to increase CPU consumption cluster-wide due to networking overheads. To address this issue, we propose to reuse previously compiled code by adding a cache at the JITServer, and we described a novel mechanism for serializing dynamically compiled code. The caching mechanism at the server further improves the performance of the remote JIT, allowing our solution to reap significant benefits in terms of startup time, ramp-up time, CPU usage, memory usage, and application density. This solution is fully implemented in Eclipse OpenJ9 JVM, and it can be tried today. So thank you. That concludes my presentation, and I'm ready to take questions.